Yeah, welcome the audience. This talk is based on the observation that the discipline software engineering is yet to mature. Mature in the sense that, like any other engineering discipline, software engineering, I expect, should give its product, that is the software, with a guarantee. Let me just give an idea regarding the content of the talk. So, brief introduction followed by some principles and techniques which we use as far as programming is concerned. And the core of the talk is the methodology for programming and the large sense software engineering, through which we try to achieve reliable software. And we will just mention about the classical phases in software development, that is software testing and maintenance, and we'll conclude. So at the beginning, let me make it very clear what exactly the goal of the talk is. It's reliable software. Maybe I should add saying that this is an ongoing experiment. We have been offering a course called Foundations of Programming in our institution for around for the last 10 years, with programming where reliability or correctness is the ultimate goal. With that, let's get to the introduction. If you see, programming even today is more of an art. And most people do programming with little direction as to the principle involved as far as reliable software is concerned. Note that an art, you can say, is learning art is more of watching others perform and maybe skills acquired by habit. What this talk is essentially stressing is that for reliable programs, programming requires, first of all, conscious application of principles. Yes, there are fundamental principles, and we need that conscious application of principles basically to have the reliability. And then you must have a systematic approach to the development. So we talk about the principles, and we talk about the systematic approach to development. Ultimately saying that, or rather this talk essentially says that programming, or finally the software engineering, is a science, not an art. Okay, note that there can be debates on that, but this talk is essentially saying it's science. We observe that learning programming many a time ends up in learning a programming language many times. So, I mean, one of the experience which I have is that when I look at the CV of graduates, even BTech computer science graduates, under the heading programming skills, most of the time observe that what is really put as the programming language is not programming. So there are no principles in programming that is explicitly put. So the point is that when we have a course on programming, what should we teach? The programming languages may come and go, but ultimately what is going to remain is programming. So we should be talking about programming, not just the tool that's a programming language. So in that sense, programming language involves orderly thinking. For example, separation of concerns is the key principle which we use basically to order that thinking, orderly thinking through separation of concerns. You can talk about many problem-solving ideas, and the key point which we stress is the modular design when you have complex problems divided into smaller pieces or modules, sort of, and ultimately ability to tackle complexity, especially when we have complex problems. And in another way, ultimately, we are stressing on simplicity, because we say that simplicity is a prerequisite for reliability. Now, when we come to the methodology, which we actually adopted in our institution, we say that we have taken, or rather, we have 3 steps explicitly as far as the programming development process concerned, starting with specification, followed by design, followed by coding. So we'll be talking about every stage, which is basically the talk on, that is the methodology. The methodology essentially has 3 steps. Again, in our course, which we have been doing it as an experiment, as I said, we essentially stress the specification and design. And in fact, we do the specification and design in the class. And only after the student is confident about the design, we ask the student to go to the coding stage in the laboratory. So we'll take up each of these stages slightly in detail. Let's look at the specification part. So that starts with problem understanding, meaning before attempting to solve a problem, make absolutely sure what the problem is. You can see that many a time, the problem specification or problem definition can be confusing. So we must be very careful. So there must be enough attempt basically in the understanding problem. And it is observed that many a time, the problem's understanding and specification is grossly underestimated. The importance of that is grossly underestimated, and getting into a lot of problems later, asking for maintenance. And also software engineering, some of the observations are 50% of the problems essentially arise basically because of not spending the amount of time required for problem understanding and specification. Now we can observe that the specification, there are some requirements. Specification should be, for example, unambiguous. It should be non-contradictory. And finally, it should be complete. Let's go into each one of them. So if you say the specification, if you find the specification is sufficiently ambiguous, note that any program will satisfy it. So if you want a single solution, the specification has to be precise. Most of the time, your problem is given in such a manner that it is ambiguous and hence the problem. And there can be possibility as far as the specifications, many of the points in the specifications contradicts, or one of them contradicts with the other. So if that happens, you know that no program will satisfy that if you have contradictory requirements. And the completeness issue, the more the specification is complete, the less the maintenance. Many times in software engineering, I feel that in the industry, the main problem, the complaint, as far as the problem which we are addressing, reliability, is that we don't have a complete specification, or the client will not be in a position to give the specification completely at the beginning. But theoretically, you can say that the more the specification is complete, the less the maintenance. And we say that we should try to have the specification even extrapolated so that we can actually incorporate that into the design, so that when the client really asks for a change, we don't have to have ultimately a design change. Design change is going to be really costly. And in this context, maybe I can maybe point out one of my experience as far as the specification stage is concerned. That's around 15 years back. I don't know, there is what is called All India Engineering Entrance Examination counseling software. So during that development, we 14 participants from 14 regional engineering colleges at that time, it was 15 years back, assembled in regional engineering college in Allahabad. And it was surprising even to me that we spent 2 full days, 14 people, and the aim was basically to have the specification. The National Informatics Center came with a draft. We debated on 2 days and finally got to that. And the outcome, according to me, is that that software ran without much problems. And let's take an example to understand that kind of a problem understanding and specification. Let's look at this small, very simple problem. Let's say divide two integers to get the quotient and remainder. And for the sake of argument, let me say that we are saying do it by repeated subtraction. Note that this itself can be ambiguous, even a very simple problem statement like this, because I said just integers, and whether the negative value is considered or not. I mean, all those issues can come, and you have to be very precise as far as the understanding is concerned. So whenever a problem statement is given, we have to understand and put it as a specification with the three conditions we have said, so that we have no problem as far as the final product is concerned. So we use an input-output format as far as the specification is concerned. And as far as this problem is concerned, we will go like this. As far as the input is concerned, let me, for the time being, even though originally it was said as integer, in the specification, let me take the problem as a dividend and divisor, the two inputs. They are from natural numbers, and I'm not considering negative values, with an assumption that I can add the sign later with an additional function, sort of. So dividend divisor, I say specify that I have natural numbers, they are natural numbers, and qualify it further, dividend is greater than or equal to 0. And note that I'm saying divisor is greater than 0, not greater than or equal to 0, knowing very well that I won't be able to divide a number by 0. So that issue of division by 0 is taken care of in the specification itself. And if the user gives a 0 as the divisor, immediately we can flash an error. So in the sense that we have to have the I'll say program in such a manner that any ambiguous or rather untoward possibility is captured by it without getting the program stuck or getting into the loop, or nothing like that should happen as far as the final reliable software is concerned. So this is the input, and similarly we can talk about the output, that the quotient and the remainder. You can see that the quotient is greater than or equal to 0. And remainder, we say it is greater than or equal to 0, and it must be less than divisor. Note that if it is equal to, less than or equal to, you can once more subtract it. So it is the remainder less than divisor. And ultimately, the input and output has to satisfy this condition, that is, dividend is equal to quotient multiplied by divisor plus remainder. Note that we have adopted such a I'll say simple mechanism basically to specify the problem, input output sort of. You can go even with English language, but you'll have to be very careful. Note that natural language is inherently ambiguous, so a judicious use of English is required in the problem specification. So that's why we did not write in English. We thought maybe we can write it something like this, and you can go to the final extreme of formal specification even by predicate calculus, which is considered to be, with which you can actually have really formal and ambiguous specification. With that kind of a specification, let's go to the design stage now. So we, as we said at the beginning, there are principles for methodology. So one of the design principles, or I'll say the main design principle which we use as far as the methodology, our methodology is concerned, is separation of concerns. So in this context, I can take Dijkstra's quote, says that separation of concerns is the only available technique for effectively ordering one's thoughts. Note that we said earlier, the principles involves orderly thinking, and that is concretized by how do we do that ordering of thinking. You can use this principle of separation of concerns. Whenever there is a problem with more than one concern, right, you try to separate it and deal it independently in a sense. So the best thing which I can quote in this context is that, let's say when we talk about an undergraduate program in computer science, we have the programming concerns of correctness, efficiency, maintainability, all those things. So you can have a course like Foundations of Programming. We say that the concerns there is only correctness. And we tell that efficiency aspect is considered in another course like data structures and algorithms, and other aspects like maintainability in a full-fledged software engineering course, etc., etc. So separation of concern is the key principle which we use as far as this methodology is concerned. And the next design principle is the classical one. We may normally say that it is by dividing the problem into smaller pieces. Here I can say that into modules. So that's the generic term which we use here. And I'll say that there's only one way to deal with complex problems. That's basically divide into smaller modules. Any complex problem, trying to deal it in complex, that's going to be difficult, or rather, you will get into trouble. So the first thing is try to divide into smaller modules. We feel that that's not sufficient. And we added this adjective, divide into smaller independent modules. We feel that this is a very important point, that is independent modules is a key, in the sense that when we talk about the complexity of software development, I don't have a clear answer regarding that, whether it is linear with respect to the size of the code, it is quadratic, or it goes exponential as the size increases. But the crucial point here is that if we have independent modules, I'll just pose the question and say that, can't the software development process complexity is linear if they are independent? If it is not independent, then definitely it's not going to be linear. So the key point is divide into smaller independent modules. Now let's get to when you talk about the modular design, the modules can be further. From there, you can come to two further principles, which are procedural abstraction and data abstraction. So whenever the computation, note that whenever we talk about computation, you have fundamentally two parts. That is, you have the data and you have the computation. You have data and computation. And whenever the computation is complex, we use procedural abstraction. And whenever we have complex data, we use data abstraction. So note that these are two fundamental principles as far as we use as far as our methodology, especially when the program becomes larger. The fundamental principles for small programs remains, but as the program gets larger, you divide into modules, and the modules can be in terms of functions or procedures, as we call, which is basically procedural abstraction. Or data abstraction, for example, you can say programming languages gives us array as a data abstraction, and you can build your own abstractions. So let's come to procedural abstraction a little bit in detail. We say the procedural abstraction separates the concern of how a procedure would be used from the concern of how the procedure would be implemented. So the key point is that it separates the concern of use and implementation. A typical example which I can quote is, let's say, printf function, print function. So when the user uses it, he or she need not know how exactly it is implemented. So, use is separated from the implementation, but somebody has to implement that. But as far as a user of a programming language is concerned, he has to remain how to use it, printf, let's say, how to write with the syntax and associated components, whatever it is, how exactly it is implemented is not his concern. So the function printf is abstracted. You're raising the level of that function, and you need to know only how to use it. Procedural abstraction separates the concerns of use from the implementation details. Again, let me take an example just to have a feel of what exactly this procedural abstraction, how exactly it's a powerful mechanism in the hands of a programmer. Let me take a small problem again for the sake of explaining this concept. Let's say that you're given a list of students and the total marks in a semester, list of students and the total marks in a semester. And you're asked to write a program to compute the percentage of students in the class having marks above the class average. So list of students and total marks are given. We have to find the percentage of students in the class having marks above average. Note that now we say that we essentially understand the problem, and I'm not explicitly writing the specification. The input is list of students and the total marks. output is percentage of students above class average. Now we'll have to see how exactly this can be handled. Note that we said it, you can have procedural abstraction, and we say that you can go to sort of a modular design in terms of identifying the subtask in the problem. It may look, the subproblems may be trivial, but this is for elaboration or as an example. So you can see, percentage above average is our final goal. And the way in which I can read this diagram is that, suppose you have a function which gives me the above average count and the number of students, then I can compute percentage above average. So it's sort of dividing the problem into smaller pieces as we go down, and we write it as a tree form. You may even call it, in the literature, you may find it a stepwise refinement. The original problem, that is percentage above average, is refined to subproblems, finding above average count and number of students. And the second thing is that the above average count can be found once you know average. If you know average, you can find above average count from, of course, the list of students that's given. Similarly, average can be found if you know the sum of the marks and also the number of students. So there is a very systematic way of dividing the problem into smaller pieces, and we call it a subtask diagram when it is a procedural abstraction. And here is a diagram which essentially raises the level at which your design goes. Maybe similar to those who are in object-oriented programming, you know that fundamentally the top level design can be a class diagram identifying the classes and interactions. And from there, you go down to lower level of design. Maybe in this context, I can stress the importance of that kind of a high-level design sort of. It helps you to have a grip on the entire problem. This is a very small problem. When suppose you have a very complex problem, getting a grip is not at all an easy thing. And in this context, let me quote. There is an article titled "Emperor's Old Clothes" by Hoare, C-A-R, Hoare. A Turing Award winner. And there was a project Elliott 503 Mark II, and the project has to be abandoned basically because he says that, let me quote, "The goals which we have attempted have proved to be far beyond our grip." And he also says that in the process of abandoning the project, 30 man-years of programming effort was wasted. So it's not an easy job whenever a problem is complex to get a grip. So we are essentially trying to have design diagrams as higher level as possible. Finally, you get a grip. This is one of the possibly subtask diagram using modular design sort of. And now we essentially write the main function using those sub-functions. Note that when we have the sub-functions, we use the specification of the sub-functions. We don't have the code right now. We only have the specifications, and that's what exactly procedural abstraction is. We have specifications, we know what it does, but we don't know how exactly it is implemented. Using the specifications, we write the main functions. Okay, so here is the main function for our problem. It is basically computing percentage. Note that I'm using scheme as a vehicle because we used it as, because it's the simplest language where it has only one data structure, that is list, and the features are also very, very small. And the students learn that in, let's say, 2 sessions sort of themselves. We don't teach them sort of. We give the manual. So here, percentage above average, bold in bold, that is the task and subtask. That's the main problem. And problem understanding stage, we find that, in fact, the input that is given, list of marks and students, we don't need the students' names as far as this problem is concerned. So from the input list, we use a get list of marks function, and we put it in list of marks. Okay, so we remove unwanted things in the beginning so that we are not bogged down with those unwanted details. So we get the list of marks. And then once we get the list of marks, I can find the average with the list of marks as the input. Note that I'm taking average at the higher level. I could have gone down to sum and the length sort of, but in order to make it simpler, so I'm saying average is found using the input list of marks. And above average count is done or got, or you calculate that from the average and the list of marks. You can find above average count. And once you have the above average count and the length, which you can find from the given the list of marks, you can find the percentage by dividing it and multiplying by 100. So note that this problem, we say that by writing this main function using the subtask, we have identified, we have a grip. I repeat that word, grip, which for a large project, it's not an easy job. So we have this methodology using procedural abstraction, identifying the subtask, writing the specification, not the code at this point of time, and using the specification to write the main function so that you have the full grip of the project in a sense. Now let's come to data abstraction, the second mechanism. And note again that abstraction, many times people have a feeling that is something complicated, but the main reason why we go for abstraction is to create a higher level where things get easier, simpler. Even though the word may look a little bit complicated, the aim ultimately is to simplify. Note that. And here again, similar to the procedural abstraction, note that abstraction is a methodology that enables us to isolate, basically the use of that data from its implementation. Use and implementation, it isolates these two possible tasks in a sense. Or rather, you can say it abstracts the details of the implementation as far as the user is concerned. So we, in our course, we create data abstractions using basically constructors and selectors, and we ask the students to write all the data abstraction, traditional data abstraction like stack, queues, trees, whatnot. Okay, this can also be constructed using this concept, so that you can talk about finally creating a data library similar to the procedural library. You can talk about data library which you can use later. As a simple example, typical databases, you can say that it is built, that's the highest level of abstraction, and that is built from records. The records, you can say every record is built from, I have taken it as prior. You can talk about a tuple containing many fields, whatever it is. And finally, each pair is implemented as a list, let's say. So you create that kind of an abstraction, and then whenever you deal with some processing, you stick to that layer of abstraction so that you don't complicate the things, you don't break the barrier as far as the abstraction is concerned, and you can do your task at that level. That is, you have created that levels so that you don't see the whole layers and gets the things complicated sort of. So you create that kind of a data level abstraction. Now, from the methodology, finally the goal of the talk is basically talking about the reliability. So let me come to that aspect. And so you can say that ultimately we'll have to prove that our program, whatever program we write, is correct. So we say the proof of correctness of the program which we finally write. As I said, software engineering, if it has to be a mature discipline, finally we have to have software with a guarantee. So that's what exactly we are talking about, proof of correctness. And the methodology which we adopt, it's basically telling that proof of correctness goes hand in hand with program development. Note that the traditional approach can be you write the program and then debug it. No, this methodology very clearly tells that proof of correctness goes hand in hand with the development. So in order to elaborate that proof of correctness goes hand in hand, let's talk about the methodology, a very systematic approach, method through which we finally, when we, at the end of the development, we have a high confidence, if not 100% guarantee regarding the correctness of the program. So let's take the same example which you have seen earlier. That is division of two numbers. You have dividend greater than or equal to 0 and divisor greater than 0. That is the input specification which you have written. Similarly, the output specification, quotient greater than 0, remainder greater than or equal to 0 and less than divisor, satisfying the invariant dividend is equal to quotient multiplied by divisor plus remainder. Now we say that you can even say that given the specification, we sort of derive the program from the specification. Now we said very clearly that it is by repeated subtraction. So that clearly tells us in the design that I must have a loop sort of. So I introduced that. So this is the syntax of the loop where you have a condition and a body. And if the condition is satisfied, this is the syntax. Semantics is if the condition is satisfied, the body is executed. So the constructor is perfectly clear. Now, there are two aspects now I have to concentrate. We take separation of the concerns, and then we look at condition and body, each one at a time. So we look at the condition now. You know that the loop body has to be executed when the dividend is greater than the divisor. Then you can subtract, otherwise you can exit. So with that observation, I can now put the condition. So I put the condition as dividend greater than or equal to divisor. Only then I can subtract, I can go inside the body and do the subtraction. It will keep on going until this condition is not satisfied. That is basically dividend becomes less than divisor, the loop will terminate. So I have designed the condition and made also sure that that is the condition I need as far as the loop is concerned. Now I can say that I have introduced these two variables. So let me finish up those things that's required. So I'll say read the dividend and divisor from the user. And we have what is called an input validation. And that validation is done with respect to the input specification. Note that if you don't have the specification, you won't be able to validate. So we are using that specification to input validate, checking that dividend is greater than or equal to 0 and divisor is greater than 0. If this condition is violated, immediately an error message is given to the user telling that you have violation of the specification. You can go very precisely which input and what exactly happens. Now we can go to the body. And once the condition is satisfied, we have already seen that it is repeated subtraction. So we subtract the divisor from dividend. And once you know that the quotient can be incremented. So the body contains two updates. Dividend is updated by subtracting, and the quotient is incremented by 1. So there is going to be an assignment, these two. That is the variables remainder and quotient. So maybe when you introduce, you have to initialize those values. The quotient initially is 0, and it is incremented as we subtract. And the remainder is initialized with the dividend, the original value. So that's what exactly we do. Remainder is equal to dividend, quotient equal to 0. That's the initialization. Note that we have changed dividend to remainder because you can see that remainder is what is keeping on changing. So it's better not to use dividend as the name there. So initialize the dividend, put the dividend to remainder, and just tell inside the body on the loop that use the remainder there. So that's a better strategy sort of. So note that change. And now you can put the content, remainder is equal to remainder minus divisor, quotient is equal to quotient part. That's it. That's the body. So note that we are going step by step, making sure that this is what has to be done. And we have the high confidence. Finally, you can maybe print the things, right? So this is the systematic way to develop. And finally, this is the program. And we can now ask, in fact, in the course, we ask the student, is the program correct? So the point is that with the whole explanation of every stage and explanation, it is, what we have done, for example, the condition we have put is correct, etc., etc. Every step, finally, the student has to feel that it is correct, sort of. And we even ask, do you really need to execute this one? Initially, they had the hangover of executing. Slowly, they finally say that, okay, through this process which we explained, I feel that it is correct. For any input, it should give the correct answer. That's the level of confidence, finally, we aim as far as from the students is concerned. So is the program correct? Okay. Ultimately, with this methodology, we feel that we can come to, maybe it is a small program we have taken, but remember, any big program is divided into smaller programs, and you can have this methodology to systematically develop programs and have very high level of confidence as far as the correctness is concerned. Now, maybe with respect to correctness, let me add, there is another aspect which any serious programmer has to be concerned, that is the proof of termination of a loop. The concepts, many times people, I don't know, we ask the students whether you have, proved that the loop you write will terminate or not. And we insist in this course, any loop you write, you must prove its correctness. Otherwise, we don't call you a programmer. So we have to tell some kind of a concept how exactly you can do. So in this respect, we have the concept of a well-founded set, which is basically a set which contains no infinite decreasing chain sort of. Let's say natural numbers. If you start from some number, if you talk about the way it goes down, it keeps on reducing, and you have the chain has to stop at 0 sort of. So we choose a well-founded set. It can be a natural number, it can be a set, whatever it is. And you have a termination measure, which is basically a function which maps the machine status to an element in the set. Maybe let me explain the concept. Again, proof of termination, just maybe symbol loop, but the concept, I hope, this example will convey that. So let's take a loop. This is the syntax, the semantics we explained. If the condition is true, the body is executed. And let's take a concrete example like you have I initialized to 0. And the condition is if I less than 0, you will go inside the body and I is incremented by 1. And the ... inside the body indicates that I is not changed. Okay, that is basically another important point. If we take this one, how exactly we use the concept? So note that, so I is initialized to 0. We now observe that inside the loop, I monotonically increases. That's a keyword as far as termination is concerned. Monotonically increases, it does not oscillate. I goes from 0 to 1 to 2, etc. In each iteration, it is incremented by 1. That implies I monotonically increases by 1 implies I will reach 10. That implies loop will terminate basically because the condition for termination is I less than 10. So note that you can take any program and finally prove that it will terminate. And in fact, this asks for a discipline in programming. Okay, note that proving correctness demands a discipline in programming, like structured programming, for example, in the sense that whenever you write, let's say, a loop, we say structured programming asks for single entry, single exit, so that the whole analysis of a loop cannot be, is not cluttered. Otherwise, it becomes difficult to understand, analyze, prove, etc. Structured programming. Then careful use of variables in the termination of the condition. So note that whatever variables you are using in the termination condition, if you clutter it with some other purposes, then you're doomed as far as analyzing what exactly happens to that variable. So careful use of the variables. And ultimately simplicity. Look for simple way to finally write the thing sort of. So in this context, when I talk about a discipline in programming, we tell the students that no global variables, because it violates the fundamental principle of, I'll say, independence. And if you have a loop and there is a go-to outside or a global variable, you find it almost impossible to analyze it sort of. So no global variables, no go-to statements, meaningful names to the variables, etc., etc. So the discipline in programming is a key thing to finally prove the correctness. If you don't have this discipline, write the loop somehow, and later try to prove the termination, it's definitely going to be difficult. So you must have that simplicity so that finally it is easy to prove the correctness. So with that design stage, 2 parts program. When you talk about the correctness, note that normally you'll have to talk about the termination of the program. So fundamentally on the loops, and then the correctness of the output. So we'll have to prove that the program finally gives the correct output given the specified input sort of. So that's what exactly we explained through a simple example. So hope that simple example, the normal charge that comes in is that for a small program, you can do it. Note that the what exactly we are trying to convey is the concept. And we feel that it can be scalable. Okay. Now let me just mention some of the aspects in coding which we know that okay, maybe again let me quote Dijkstra. He says that the tools we are trying to use and the language of the notation we are trying to express or use to express or record our thoughts are the major factors determining what we can think or express at all. And telling that program into a programming language, not in it. So when we have the design, normally we say that have the design in a notation or the language independent of the programming language in which ultimately you're going to have your program implemented. So your design is independent of the programming language. You can take the design to any programming language later. Ideally, there can be, of course, limitations. For example, suppose you have a functional style, you'll have to use that startup. Imperative style, you have to use that. But fundamentally, the concept is that try to isolate your design from the implementation details of the programming language. So in this respect, maybe you can note that a restricted language can hide the best algorithm from us. Example, language without recursion. For example, Fortran 4 did not have recursion, and you cannot have elegant recursive solutions that's available at that time in that language. So a restricted language can hide the best algorithm from us. And a restricted language can or limits our thought process. Let's say that a language without a construct for non-determinism, in which normally normal programming, imperative programming languages does not give you. Let's say the syntax of a non-deterministic construct is something like this, where it says you have condition action pairs. What exactly non-determinism says is that if any of these conditions are satisfied, you can have the corresponding action executed. Not it is sequential. I mean, you can any condition satisfied, you can execute. Typical example is in an ATM, where let's say you are asking for withdrawal of 1,000 rupees. Note that it can be 1,000 rupee notes or 2 500 rupee notes. So if the machine has 2 500 rupee notes available, it can dispose that. If the machine has 1,000 rupee note, it can dispose that. So that's the way in which we write. So the output can be non-deterministic. But suppose you don't have this non-deterministic construct, you have to have a sequential order, like if this condition, else this condition, else if this condition. So that's putting an explicit order, which is not really necessary, sort of. And now coming to another aspect, a cluttered language can hinder us from thinking clearly. An example is consider you multiplication of two numbers and say the notation, the language we use is Roman numerals rather than the decimal numbers. Try to multiply two large numbers, represent it in Roman numerals, and try to multiply it and compare it with the decimal numbers. Decimal numbers are much, much simpler. Now let me come to testing. Gain coding Dijkstra program testing can be a very effective way to show the presence of bugs, but it is hopelessly inadequate for showing their absence. It can never be a proof of correctness. So fundamentally, if you are concerned about correctness, reliability of program, what we are saying is that programmers should try not to introduce those errors to start with, meaning you have to spend enough time on the problem understanding, specification, design, prove it, the design is correct, and then finally take it into code. And as far as maintenance is concerned, as we said earlier, the more the complete the specification, less the maintenance. And in this context, maybe I can tell our experience. Even the computer science and engineering department website, it was created 10 years back. It is still running. And we had the clear intention of less maintenance or design ruggedness. And we know that we don't have people regularly for maintenance. And you may be surprised that with the student into the project, we took more than 1 year, when you know that a website can be created in a few days. Note that. But the indication, what I wanted to stress is that 10 years back we are still using that same website design at that time, computer science and engineering website. Ultimately, to conclude, we say that to have reliable software, the product is not just the code. It must contain the components, like you must have a specification, so that note that you can have the cost estimate or the time estimate of a software project only if you have a specification, complete specification. Otherwise, you cannot do that. Or I'll say you cannot do it precisely. So you have to have a specification and you have to have the program. It may be, the design plus code in whatever programming language. We here meant most of them, the stress is on the design. And of course, it will have finally the code in whichever programming language you wanted to convert or translate it into. And the final thing, of course, is the proof of correctness, which is basically telling that the program satisfies the specification. So note that ultimately the product has to be these three components, and normally we may just give the program. That's not sufficient. You must have a specification, you must have a program, you must also have the proof of correctness. In our course, we ask the students to write even in English sentences or argue. We say that effective use of English language is sufficient for the timing. You can have the formal proof using predicate calculus and associated things, or rather classical algorithm proof, which we do in our courses sort of. But in this course, we said effective arguments is to start with, that is sufficient. I'll say effective use of even language English, which is inherently ambiguous. So I'll just mention one or two of the references which I have used as far as the talk is concerned. We have been looking for a textbook as far as this course is concerned, and we found Structure and Interpretation of Computer Programs. I should say that this was the origin where we started, but we have gone much beyond that. But the concepts of procedural abstraction, data abstraction and modular design is there in that textbook, so we still hold on to that. And the key principle of separation of concerns, it is mentioned by Dijkstra in the article on the role of scientific thought. And we mentioned about the proof of termination and the concepts there. It is there in the book by Benjamin C. Pierce, Types and Programming Languages. There are many other articles by Dijkstra, which I have taken many quotes, and it is all available in University of Texas, Austin, in this site. All the articles by Dijkstra is archived by them. That ends my talk. Thank you for listening. The first question here is from Sharon. I don't know how to pronounce, so I'll leave it there. Sharon. He asked, in the web and application field, in the work sector, what's the difference between a software engineer and a full stack developer? I'm not sure how exactly to differentiate, but from this talk, what exactly I can say is that suppose we say software engineer, my take is that if we consider engineering as a discipline, like any other engineering discipline, you go to shop and you buy any, I'll say, electronic equipment, you get a guarantee card. So ultimately, I'll say that software, whatever it may be, application software included, you should have a guarantee. Whatever name you call does not matter. Finally, the product, whatever be the product, must have a guarantee that it satisfies the specification. I don't know whether, I should have a further question onto that. Maybe I'll take the next one. So when you have a problem to face, as simple as adding a new button to an application, the separation of concern comes into play. And does separation of concern goes hand in hand with testing? No, I don't know whether I got it right. So, but I can tell very clearly, in fact, we would like to say that if you adopt this methodology, we clearly said the proof goes hand in hand, and we don't have testing. Ideally, we don't test, because with the design itself, we have already proved that it is correct. Okay, so ideally, I'll say there is no testing. And remember, testing cannot be accepted as a proof. Finally, you cannot prove by testing. Dijkstra's quote. And let me come to the next one by Vivek. Finally, the question is, do you think the next generation of programmers takes program specification seriously? Ultimately, the point is that if you don't have a specification, what are we doing? I'll stop at that point. Without specification, what are we doing? We should be very clear what we are doing, and that is actually given by the specification. Note that. So any project going ahead without the specification, with the completeness, unambiguous, non-contradictory things, definitely will land into trouble, whatever be the project. That's the way in which I can possibly answer to that question, Vivek. And then Vellur Shashi Kumar, is it true that future is without coding and running the predetermined workflows? I'll say, Shashi Kumar, definitely there are efforts regarding generating code from specification in compiler. Well, that's my area. We know that lexical analyzers are generated from specifications. And similarly, syntax analyzer is generated from specifications. You don't have to write code, you have to give the specifications. But it requires effort as far as any new problem area to find an appropriate formal language to specify. And if you can do that, finally, there is a possibility for generation. So right now, you have areas where you have formal language to specify. From there, you can automatically generate, like lexical analysis and lexical analyzer and syntax analyzer and compilers. Now people don't write it, it is generated from specifications. Now Shijin, Copilot is an AI-powered code generator. Yeah, ultimately code generator, I mean, you need specification, formal specification, repeat formal specification to have code generation ultimately, right? Otherwise we have to write. Okay, AI creates program with the OpenGPT from symbol descriptions. Descriptions, Vivek, I'm doubtful. I mean, I'll say that, okay, the specification, when I say, we have put 3 conditions: unambiguous, non-contradictory, complete. I'll say any mechanism through which you satisfy these conditions, I can consider it as a specification. So symbol descriptions, I'm not sure what exactly that is. Okay, if these conditions are satisfied, yes, I'll take it as a specification. Then you can proceed further. Okay, I think that's all the questions I can find.
Yeah,